powerful analytical tool. The theory of chromatography can be illustrated when a mixture of two dyes, one blue, one orange, is placed on a column of a special material. Orange molecules tend to stick to this material better than blue molecules. As the column is continually washed with a solvent, time-lapse photography clearly shows how the blue molecules are separated from the orange molecules, as the blue substance partitions itself preferentially in the moving solvent and is collected as the solvent leaves the tube. The orange substance is still at the top of the tube and can now be recovered. Gas chromatography works in a similar fashion, except the separation occurs in the gaseous phase, not the liquid phase. Here, the sample mixture, represented by compounds A, B, and C, is injected into the gas chromatograph using a microliter syringe. Only the smallest fraction of a drop is injected, and it is quickly vaporized. The vapors are swept into a long tube by an inert carrier gas such as helium. The tube is surrounded by an oven to keep the sample in the gaseous form and is packed with a solid material to which substances A, B, and C adhere with varying degrees of affinity. Substance B, for example, because of such molecular characteristics as polarity, may move quickly through the column, swept right along by the carrier gas. Compound A might have a stronger affinity for the solid material in the column and move more slowly. Compound C, with yet a stronger affinity, moves the slowest. When a band of purified material exits the tube, a detector records its presence on graph paper as a function of the time on the column, called the retention time. If a known sample of DBCP has the same retention time on the gas chromatograph as substance C, then compound C may be DBCP, or it may not. While a gas chromatograph can separate components of a mixture, it cannot positively identify substances. We need a mass spectrometer to do that. The theory of mass spectroscopy can be illustrated when a paper clip is dropped through a magnetic field. Animation shows how the paper clip is deflected by the magnetic field. In a mass spectrometer, molecules of a compound pass through an electrical discharge, which breaks the molecules into smaller charged fragments called ions. These ions then pass through a magnetic field, which, like the paperclip analogy, has the effect of deflecting the ions. Lighter fragments are deflected more than heavier ones. An appropriate detector and recorder then chart the mass of these fragments, a graph of which is unique for each substance. So while the mass spectrometer cannot separate mixtures, as can the gas chromatograph, an identical mass spectrograph of a known and unknown definitely proves the two are identical. The computer stores all of the information generated by the gas chromatograph and the mass spectrograph so that it can be recalled and examined at any time. These three instruments provide a powerfully sensitive tool which can accurately identify and quantify diminishingly small amounts of sample. This unprecedented analytical sensitivity has advanced far beyond the sensitivity of the tools of toxicology to tell us what low-level residues can do to us. Fred Schreiber, a biologist at Cal State Fresno, emphasizes the qualitative nature of animal testing.
Animal testing for carcinogenicity and mutagenicity is basically an either-or type of test. What you want to do is determine whether or not a particular compound is carcinogenic or mutagenic, or whether it's not. The tests, in order to determine this, generally use a relatively small number of animals in order to do it for a financially reasonable sum. The number of animals can vary anywhere from in the tens to 50 to maybe several hundred. Animal tests can only give you a rather general idea as to whether it is a potent or a weak carcinogen or mutagen. When only a small dose shows a marked effect, then you can assume that that compound is rather potent. Normally what you do, however, is you use animals that are very sensitive and predisposed to cancer, and then large doses, so that you can find out whether it is a carcinogen at all.
But what of the criticism that just about any compound given in large enough doses will give cancer to these especially sensitive animals?
The charge that any compound will cause cancer if you use enough of it is a myth. It's simply not true. In fact, there are many experiments numbering in the hundreds with both in vitro and laboratory animal tests that have come out negative. No effect at all has been shown. You can give the maximum tolerated dose to an animal and still not come out with any known or any observable carcinogenic effect.
But if humans are exposed to a tiny fraction of the doses test animals get, are they safe or at risk? In other words, is there a no-effect level, a threshold dose below which the compound will not cause cancer?
Today there is no definitive evidence as to whether or not there is a no-effect dose of chemical carcinogens and mutagens. We simply can't test. We can only give our best guess as to whether or not there is such a thing. Unfortunately, some people's best guess says there is a no-effect dose. Other people's best guess says there is not.
Animal testing requires a large investment of talent, time, and money. Bruce Ames, a professor of biochemistry at UC Berkeley, has developed a rapid and inexpensive screening test to determine if a chemical can cause mutations with the DNA of cells. A special strain of bacteria developed by Ames is, unlike most bacteria, unable to produce its own histidine, an amino acid necessary for its growth. A small amount of this bacteria is mixed with the test chemical in a nutrient medium. The bacteria is incubated, and if the chemical is, in fact, a mutagen, it causes the bacteria to mutate to a form which does produce histidine and can, therefore, multiply. The Petri dishes are checked after incubation to determine the extent of bacterial growth. The greater the bacterial growth, the more potent a mutagen the test chemical is. The test is fast, cheap, and 90% accurate. But critics of the petrochemical industry think these advances are too little, too late. Dr. Samuel Epstein is professor of occupational and environmental medicine at the University of Illinois.
In 1940, we synthesized and manufactured about 1 billion pounds of synthetic organic chemicals every year. By 1976, this figure had reached 300 billion pounds of synthetic organics. And I should stress that the overwhelming majority of these chemicals have never been tested for their ecological effects, let alone for their public health effects. With the exception of special purpose regulations such as for pharmaceuticals and for drugs, the overwhelming majority of these chemicals are virtually totally untested.
Professor Epstein suggests in his book, Politics of Cancer, that petrochemicals are responsible for what he believes to be an epidemic of human cancers.
There's overwhelming evidence that we are in the middle or at some early stage of major increases in the incidence and mortality of cancer. Last year, 400,000 people died of cancer. 1 in 4 of us gets cancer, 1 in 5 of us dies from cancer. From 1933 to 1970, looking at age-standardized cancer mortality rates, there was an 11% increase in age-standardized cancer mortality rate. Cancer is the only major killing disease which is on the increase.
Dr. Bruce Ames, who developed the Ames Rapid Screening Test, disagrees.
So, there really isn't a cancer epidemic. Cancer goes up. Cancer is a disease of old people, so the older the population gets, the more cancer you get. So if you cure other diseases and people get older, then a higher percentage of people will get cancer. So if you age correct it, which is what all the people in the field do, then and look at the cancer incidence, then really there isn't that big an increase, except for lung cancer, which we know is due to cigarette smoking. So all the women who started smoking after the Second